Sorry, I'm getting a lot of stuff in the chat. Can you announce that some of us are doing a study on Zoom today at 2 o'clock? There, I did. There's a Zoom today at 2 o'clock. The link for the Zoom is in the group me. If you want to do a study session, you can join at 2 o'clock. If you can't make that time work, you can do another study session. I'm pretty sure you guys can set up Zooms for 45 minutes to an hour. And I don't know if you can go beyond that. Somebody was asking me this morning as well. Yeah, students can set up Zoom. So Zoom at 2 o'clock. All right, yeah, if you need to meet with me, set up an individual Zoom, I'm happy to do that. But back to these announcements. Chapter 3, homework due Friday. I encourage you to do it before the exam, though. I think it will help you a lot. I just wanted to give you some extra time in case you need to study on some other things for the exam. Quiz today. Quiz 3, 5 multiple choice questions due by the end of the day. Don't forget that. You can take a screenshot of this if you don't want to write all this down. Exam 1. The biggest thing I want to remind you of is please do not forget to sign the academic integrity form. Okay, so remember I have those at the beginning of all the quizzes. This puts me in a really tough spot if someone forgets to sign that. I don't think anybody would intentionally not sign it. I think you all would just, if anybody forgets, it's just because, like I said, you forgot. But please just immediately do that. I've had students in the past, they forget to sign that because they just get busy working the problems. And I know you want to get to all that, but it takes 2 seconds. Please do that. Don't forget. Okay, on the exam, you will have to do this one time. There's going to be a couple complex conversion problems, and at least one of them, I'm going to have you take a picture of your work and upload that picture to the exam on Blackboard. All right, so there's an app. I highly suggest, has anybody ever used the Scannable app before? Anybody ever had to do this for other classes, take a picture of your work? This is a free app. I think I'm pretty sure it's free. Last semester, a bunch of students used it and raved about it and loved it. You can take a picture obviously on your phone. So I am allowing you to use your phone for the purpose, only for the purpose of taking a picture and uploading that to the exam. But here's why the Scannable app is nice. It's blue. It's a blue app. I think it has a butterfly on it or something. If you download that, you can hover over the exam and it'll save it as like a PDF for you. And I'm asking students to only upload pictures as a JPEG or a PDF. And so it freaks students out. A lot of students are like, how do I save it as a PDF? I don't know how to do that. If some of you are familiar with, Microsoft and things like that, it's very easy to export your document. If you click save and export, you can always export things as a PDF. So you can always upload a picture into Microsoft Documents, export it as a PDF, and upload that to Blackboard. I know that takes a few moments to do that, though. And you can also do that on Apple Notes, hey, Heaven says. So thank you. If you guys have tips, discuss those in the group me or reach out to me if you don't know how to do this. But I encourage you to use this Scannable app. And you'll upload that as a JPEG or a PDF. There'll be specific instructions on that. Make sure the lighting is good. Make sure you get all your work in the picture because you can only upload one picture. So don't stress about that. You have 2 hours to take the exam, which is more than you would have if we were face-to-face in class. It's just that it's sometimes if you haven't done it before, it can be a few steps. All right. It's called Evernote Scannable, Bradley says. There you go. Thank you. 8 a.m. group will be password protected because they're getting on before you guys to take it. That doesn't apply to you. Okay, there will be no password for the exam. You guys will just be able to get on and take the exam. And when do you get on to take it? You will get on exactly at your lecture time. Okay, so 10:50. And you'll have 2 hours, 10:50 to 12:50 to take it. Okay, and then the exam will auto shut off. Okay, so we won't have Zoom that day. Don't come on here. Log on to Blackboard. The exam will be open right on time and you can begin and you'll all take it at the same time. Okay, dry lab. I want to talk about this really quick. I heard there was some confusion and discussion about reporting numbers in scientific notation. So I want to talk through that. That was a 3-point problem. I'm going to jump, by the way, before I jump over there, I posted the key. If you want to see how I worked out all the problems on the dry lab, I posted this to Blackboard. Okay, so you can get on and see that as well. It's in the labs folder. So let's go over here to the dry lab really quick. I was working a problem with some students earlier. Right here. So on the dry lab, I ask you to do 1A, and I ask you to input all your answers in scientific notation. The reason I'm going over this is because we may have to do this again on future assignments. And I think if I explain it, it'll clear up any confusion with this. So let's just do the first one, and let's report this in scientific notation exactly how I wanted you to do it on Blackboard. First, we need to convert milliliters to centiliters. So we need a relationship between milliliters and centiliters. I know there's 1,000 milliliters in 1 liter. I know there's 100 centiliters in 1 liter, and because these are two equal, both to a liter, they equal each other. There's 1,000 milliliters in 100 centiliters. Sorry, sometimes it cuts me off on the side. Okay. Now, if you want to simplify this, you can. Okay, you could simplify 1,000 and 100 to 10 milliliters equals 1 centiliters, but you don't have to. So now let's work the problem. You've got 1,055 milliliters. We're going to convert using this relationship, 10 mil, or you can use the other one, this top one, 10 milliliters for every 1 centiliter. Okay, so divide by 10, 105, oh gosh, 5.5 centiliters. There it is. Okay, so that's the number. And then on Blackboard, I said report all your answers in scientific notation. So that's where a lot of people miss points is you put it in as a standard number. And I wanted you to type it in scientific notation. Remember the rules for scientific notation, you've got to make this number between 1 and 10. So we're going to move the decimal 2 places to the left. And now we have 1.055 centiliters. This is a number. Oh, we got to put the times 10. Times 10. We move the decimal 2 places left, so the exponent increases. Times 10 to the 2, and we have that many centiliters. Okay. Now on Blackboard, the instructions. I know there were a lot of instructions on this, and I'm sorry for that. But what I wanted you to do, I said scientists use the shorthand notation E to indicate times 10 to the power of something. So I just wanted you to write this as I said, include 3 decimal places. I told you exactly how many decimals on every problem. So it would be 1.055. And if I say 3 decimal places, I don't mean only include the decimal places. You've got to still include the number that's left of the decimal, but 3 decimal places to the right of the decimal. Okay. So there are those 3. And then it should have been E2. Okay. E means for times 10 to the power of. And then 2 was your exponent. Do we still get a formula sheet? Come on, I'm reading in the chat. Yes, you'll have a resources page is what I call it. It'll have a periodic table on there for you, and it'll have a couple of your temperature conversion equations and any other, I haven't decided what all I'm putting on that yet, but any other equations I feel you may need. But you also have, access to your notes and things. So, but yes, the resources page will be in the exams folder. I'll create a folder on Blackboard for exams. Another question in the chat. So when the decimal place moves to the right, it's a negative exponent, right? Not always. It just means the exponent decreases. Okay, so sometimes it could decrease from a +6 to a +4. That's still a decrease, but it's still a positive exponent. So don't think it's just a negative exponent. It's just that when the decimal place moves right, the exponent decreases. Okay, so this is what I wanted you to do for all of these problems. So if you missed, here's what I hate. Here's what I hate about Blackboard. And I understand this for you guys. Some of you guys are working your tail off on these assignments, spending a lot of time, putting in a lot of effort, and then you're freaking out because if I just type it in one wrong way, wrong thing, I get no points for my answer. And I understand that's the crappy part about Blackboard, okay? And that's why I don't like doing chemistry on Blackboard. So, but that's what we have to deal with. And I really do try to give as many instructions as possible where I know it's got to be a specific answer. You got to enter it a specific way. And so please always, if you have questions about those instructions, reach out to me beforehand. And I'm happy to clarify any of that. And I wish I would have done this before the dry lab was due now, because I didn't realize how much trouble it would cause with some of that reporting, okay? So if in future I ask you to do this, here's what I mean. Here's how I want you to format your answer. I'll tell you how many decimals, and you put in your exponents like that. Questions. In the chat, do you know how many questions and are they all multiple choice? So you'll have 10 to 15 multiple choice questions on exam 1. And each multiple choice will be worth 3 points. So 30 to 45 points of exam 1 will be multiple choice, okay? So about a third to a half of the percent of the exam. In regards to the dry lab this week, is there a pre-lab? No pre-lab on the dry lab this week, okay?
And
normally
the lab will be due Sunday.
Yeah, this dosage lab is due Sunday. So I'll remind you of that after the exam. I really just want you guys to focus on the exam. Okay. Great questions. All right, so let's go back to my announcements. Discussion board questions. So if you responded to the discussion board questions, great. You got some bonus points. It's now too late. That opportunity is done. You had to respond by last night because we're going to look at those right now. So I'm going to share my screen to my desktop. And I want to briefly talk through these discussion board questions. So I got so many little windows on my, there it is, discussions. I'm going to share, here we go. Okay, can you guys now see the discussion board questions? Okay, so really great feedback. We had like 77 responses. That was wonderful. Number one, I'm going to talk through these real quick. Formation of a precipitation involves a change from things that are liquid to forming something solid. So why is this considered a chemical change and not a physical change? Anybody want to answer that? Why is precipitation a chemical change, not physical? Seems like we're just changing state of matter from liquid to solid, but that's not all that's happening, right? What you have to know is you are altering the chemical composition. You're forming a brand new chemical compound, and that is the precipitate. It's a new chemical. So things are reacting and you're getting a new compound. So the chemical formula or the chemical composition of your reactants is changed, it's altered. That's why it's a chemical change. So don't be deceived. Just because some things are liquid and then you get a solid, it's not always just a physical change. You've got to ask yourself about the chemical composition. Okay, how is the formation of a precipitate different from the process of freezing, which changes, in which a change from solid to liquid occurs? Or sorry, liquid to solid occurs. So I saw one response. A student said, well, because when you freeze liquid to solid, that implies an absence or an input of heat. So a change in heat is a chemical change. But you have to keep in mind, freezing, you always have to ask yourself, is the chemical composition changing? Like water, okay, water that's liquid to water that's ice, frozen solid, it's still water. The H2O is the chemical formula for that molecule. So you always have to ask yourself, words like freezing, melting, boiling, evaporation, these are physical changes, not a chemical change, okay? And what a substance that freezes, we just answered that, it's physical. Okay, number two, considering the process of dissolving a packet of sugar into some hot coffee or tea, is this change chemical or physical? Dissolving anything. Here the example is sugar and hot coffee. When something dissolves, is that chemical or physical? What do you guys think?
Is that chemical?
Okay, we got to vote for chemical. Heaven says physical in the chat.
Physical.
Physical. Okay, a lot of people are saying physical. Why is that a physical change? It is a physical change. Is that sugar molecule altered? Do we have new substances, or have we just mixed the sugar and the original coffee molecules or tea? Okay, it's just mixed. So this is why it's a physical change. Now your coffee tastes sweet, but that's just because we have now mixed the sugar molecules into the coffee or the tea, but neither of the original substances are altered. Okay, they're just mixed. So that's a physical change. So anytime we dissolve something, the molecules of sugar are just spreading out in the hot liquid. All right. So that's a physical change. Number three, currently when my daughter asks for juice, I fill a cup halfway with apple juice and then dilute it with some water. Don't judge me. She doesn't need all that sugar. Does a physical or chemical change occur when I dilute the juice? So again, juice is just the example. What I'm getting at is, are diluting things, is that process physical or chemical? Okay. Dilutions, what do y'all think? Physical or chemical? The answer is across the board. We're pretty consistent on this one. Just diluting something with water is physical. Okay, again, you're just mixing substances. I'm not altering the apple juice. Still tastes like apple juice, okay? Just a little less sweet because the concentration's diluted by the water. Okay, so dissolving and dilutions are physical changes. Things like melting, freezing, physical changes. There's key words usually. Words that imply heat is being added that are chemical would be words like roasting, exploding, cooking, okay, toasting. Those imply that heat is being applied in a way that's altering the chemical substance. Questions on that? I wanted to go over that because I may ask you something about dilutions and dissolving whatever on the exam. So I want you to be ready for that. Okay. Let's get into the stuff for today. I think that was all the announcements that I had. And now we're going to jump over to this one right here. So we're going to continue. Sorry, I'm having to scroll down. I'm sorry. We're going to continue with ions. So we finished talking about transition metals and how they can form different ions with multiple charges, so on and so forth. And now we're going to pick up with how to write the names of ions and compounds. And this will conclude all the material that'll be on chapter or the first exam. Somebody asked me, what about lab material, like the dry lab and the detecting signs of a chemical change? Yeah, anything from the labs is material that could also, you need to be accountable for that material on the exam. Okay. All right. This is the last slide we ended with last Thursday, where we wrote out the symbols for ions, okay? And I want to make a distinction. Somebody asked me this question at the end of lecture. It's a very good question. How do I know if I'm supposed to write the name of the ion or the symbol? Like, how do I know if I use Roman numerals or if I don't? Well, Roman numerals only have to do if it's a transition metal. But if I tell you to write the symbol, okay, the key word here is symbol. Okay, if I tell you to write the symbol, that's where you're just writing the elemental symbol and the charge. If I tell you to write the name of the ion, then you're going to write out the full name. And I'm about to teach you how to do that. There's another practice problem. I may make a video through some of these extra problems and post that to Blackboard, but I encourage you to try to work some of these extra problems for practice on your own. And anyways, I'm going to skip over that for now because we want to get to this. Okay, writing the names of cations, writing the names of ions. So this is not just writing the symbol, this is how do you write out the full name. And this is leading up to how do we write the names of compounds, okay? And we'll see what a compound is in a minute. All right, well, if you're gonna write the name of a cation, you need to first ask yourself, is this a main group cation or transition, okay? So we've got two classifications. Number one, main group. Number two, transition metal cations. So which ones are the main groups? I think I have a periodic table right here. I'm going to highlight in red our main group cations. Those are main group 1 and main group 2 and main group 3. Any elements in these groups are main group cations. We name them differently than transition metal cations, which are all these metals right here. Okay. So main group. It's very simple. If this is our cation, we just name the element and we put the word ion. No Roman numerals. So K plus is we name the element. Potassium, add the word ion. Magnesium, Mg2 plus. Name the element. Magnesium, add the word ion. Something from main group 3, aluminum. Name it, add the word ion. Okay? So that one's as simple as it gets. Name the element, write the full name, and then add the word ion. So if I said, name these cations and their main group, that's how you do it. All right, transition metal cations are different. This is where you have to use Roman numerals. By the way, I just want you to ignore this right here. We're not going to talk about the old naming system. We're just going to use the new naming system. So if I have Cr2 plus or Cr3 plus, notice this is the same element, chromium. And we could get a +2 or +3 cation. This is a transition metal. So we have to denote, is it +2 or +3? And when we write the name, and that is where the Roman numerals are going to name the element, chromium. Then in Roman numerals, put 2 if it's a +2 and add the word ion. For chromium 3, name the element, put the 3 in Roman numerals, add the word ion. Okay? Any questions on how we name? That's it for naming cations. It's either a main group or a transition metal, one of the two. Those are the rules for naming it. Okay. Anions. All right. How do we name anions? Remember, anions, how do you become an anion? Do you give away or do you receive electrons? Anions. Do you give away? You receive. That's right. So these are elements that have gained or received an electron, and now they have a negative charge. Okay. You notice that with their symbol, they're all negatively charged. So these are the elements that these corresponding anion names go with. So if we have bromine, chlorine, fluorine ion, notice these are all main group 7. These are the halogens right here. And these are our main group 6. So by the way, where are anions going to be on the periodic table? If I scroll back up to that periodic table, all your anions, I'm doing yellow, all your anions are like right up, I thought that was going to be yellow. These are all your anions, okay? So these are the elements that we're talking about right now. How do we name them? They're typically the left side, and there's most of them. I might have not highlighted 1 or 2. Some group 5s in here. These receive electrons. So notice, as you write the name of these, the name ending is different. So you're going to name the element. So if it's bromine, it'll be bromide, okay? The name ending is IDE. We change the ending of the element name to IDE. We notice we do that for oxygen and sulfur as well. Oxygen becomes the oxide, and then you add the word ion. Sulfur becomes the sulfide ion. You only do this for anions, not for cations. Okay? Questions there? That's pretty simple. Now, guess what? I'm about to remind you of your polyatomic ions. You have some other anions on this chart. We do not use the IDE rule for these. Polyatomics have a set name, and we don't change the name ending if it's an anion to "ide." This is just for elements right off the periodic table, not for polyatomic ions. All right, so keep that little subtle difference. Remember that. By the way, don't forget your polyatomic ions. There's 11. I reminded you of this day 1 of class, and I'm reminding you again now. The ones boxed in red you need to know. There's 11, and you need to know both the name, okay? So for example, hydronium, and you need to know the formula. You need to know both. And the formula includes the charge, okay? So you see how most of these, there's only 2 that are cations, ammonium and hydronium. All the other ones I'm asking you to remember are negative charged. They're anions. And we will not, for example, what I was saying is we do not take nitrate ion and call it the nitride ion. Okay, then you're just talking about nitrogen. If this is in a compound and we're going to name it, you call it nitrate. Okay, so the polyatomic ion names are set, and we'll just use those when we name compounds. All right, questions on these? I'm going to move on to the next thing. This is just rote memorization. There's really no other way around it. Okay. Okay, writing ionic compounds. So now we're going to talk about a compound. So before I even get into this, what is a compound? Anybody have a thought on that? How is a compound different from an ion?
There's multiple elements in it.
Yes, remember how we had to learn how to classify matter? This was week 1 of class. Elements, you cannot break down any further. They're as simple as it gets. Compounds are a combination of more than 1 element. Could be 2, could be 3. And compounds overall, the first thing we can note is they're generally formed between a metal and a non-metal. Your metal will always be your cation. Your non-metal will always be your anion. Okay? Metal and a non-metal. Could be a transition metal, main group metal, and then a non-metal. And it could be a polyatomic as well in there, okay? And compounds, one other thing I want to note, these are always neutral, okay? Ions are charged. Compounds are the combination of ions, especially ionic compounds, and they're neutral, okay? The positive and negative charges will always balance out to 0. And we'll see how that happens, okay? So for example, 2 metals and non-metals, 2 examples coming together. The first one, what if we have a potassium ion and a fluorine ion? So potassium and fluoride. Well, we know potassium is the metal. That's the cation. It's got a plus charge because it's main group 1. And remember, any element in main group 1 is going to give away its 1 valence electron. Okay, we see the 1 valence electron down here. Fluorine is main group 7. So remember the electron dot structure for fluorine right here? It's got 7 dots around it. It would really love to receive 1 more electron. And when it does so, it gets a full set of 8. And these come together and they form KF, potassium fluoride. We're going to go through the naming later, so I'll walk through that in depth. But potassium Oh, no E on that, sorry. Fluoride. Potassium fluoride. So that's an example of a ionic compound, a metal and a nonmetal. Another one, calcium and oxygen. Calcium's got a +2 because it's main group 2. Oxygen has a -2 because it's main group 6. It receives 2 valence electrons. So we end up with calcium oxide. Calcium oxide, example of an ionic compound. Okay. And again, these pictures down here are just showing you from the viewpoint of their electronic valence electron symbols or structures, dot structures, how these things come together. Okay. Potassium, again, is going to give this valence electron to fluorine. Calcium is going to give both of these valence electrons to oxygen. And then remember when you write the electron dot symbol for the ion of a main group 1 or 2 or 3, or really any cation, you're going to, oops, sorry. It's common to write them with no dots, okay? Even though underneath they have a full set of 8, this is true and they're stable. It's more common to write them with no dots so that we understand they've given away all their valence electrons. All right, questions on any of this so far? So let's work on writing some ionic compounds. So we're going to switch things around. We have the same elements as the previous slide, but what if potassium is going to go with oxygen? Because sometimes you have ions that have different charges. So what was nice about these up here is you had a +1 and a -1. You had a +2 and a -2. Those match, right? Well, sometimes it's not always that easy. Sometimes the charges, the numbers on the charges don't match. And that's what the case you have here. When potassium, it only wants to give away 1 valence electron. But there's a problem because oxygen wants to receive more than 1 valence electron. It wants 2. So what do we do? How are we going to form a compound between these things? What kind of products are we going to get in ion form if we were to write the ions? You would get 2K. That's right. If we have 2 of these atoms and each one can give away 1 valence, oxygen is happy to accept both of those. So we're going to get 2 potassium ions, and then we'll still have oxygen with its original 6, plus now it has received 1 more and we get a -2. So there's ways to manipulate some of the numbers here, not the charges. We can never manipulate the charges, but we can manipulate the number of atoms that we have. All right, so these are going to come together and the compound that they form is K2O. The subscript of 2 indicating you have 2 potassium cations in this compound. How would we name this one? Any guesses? I haven't walked through the rules yet, and we will. You always name the cation, then an anion, so potassium oxide. And we drop the word ion. Again, we'll get to all that in a minute. Okay, another issue could be what if we have calcium and chlorine? Calcium has 2 red dots, 2 valence electrons. It wants to give away both. It's not satisfied if it only gives away 1. It needs to give away both. Chlorine, though, has 7 valence already. It's a halogen, main group 7. So chlorine only wants to accept 1 valence electron. So again, how can we manipulate the number of atoms we have here so that everyone is satisfied in the end? What can we do? Yeah, I'm seeing it in the chat. We need to have 2 chlorines. If we have 2 of these, now each chlorine can accept 1. And calcium can give 1 electron to each of those chlorines. And we form Ca2+, and we get 2 chlorine anions with all the dots. And together, these form what compound? Well, keeping in mind how many cations and how many anions we need, it would be calcium, CaCl2, calcium chloride. Why is it Ca2+? Great question, Bradley. Does anybody want to help out here? Anybody think they got this one?
Is it because it gave away 2 valence electrons?
That's exactly right. Unlike potassium, potassium only gives away 1. Calcium gives away both of these. So now there's a proton-electron charge imbalance. How many protons does calcium have? We could answer that question really easy. Calcium is 20 right there. So it's got 20 protons, 20 protons, 20 positive charges, and starting out as a neutral element, it's got 20 electrons. But when it gives those away, now we only have 18 electrons, okay, which are the minus charges. So 20 positive charges and 18 negative charges adds up to a balance of +2. That's where the +2 comes from. Okay, this is all stuff we walked through last Thursday. Great question, though. All right, I'm going to teach you one little thing, because there's going to be times you have to write compounds, and you're looking at the ions. This is on your Chapter 3 homework, by the way. And you're looking at the ions, and you see what charge they have, and you're going to ask yourself, okay, how many cations do I need? How many anions do I need to get a neutral compound overall? And sometimes that can be confusing. So I'm going to teach you, it's called the switch trick. Some people like it. Some people are like, I don't need that. So maybe it'll be helpful for you. But let's look at this. The switch trick is this. We look at the charges on our ions, and then we switch those numbers, and that tells us how many of the opposite ion we need in the formula. Okay, so let's read through this. The charge on this ion is the anion. Okay, this is phosphate, by the way. If you remember from that polyatomic chart, PO4, this is phosphate. And it's got a -3 charge overall. So that's going to be the number of cations, right? So this arrow is pointing to the number of magnesiums, which is the cation in this case. So we're going to need 3 magnesiums. And if we apply the switch trick to the charge on the cation, right? The charge on this cation, is going to be the same number of anions that we need, right? Right there and right there. And this is magnesium phosphate. So that is the switch trick, and it applies every single time. I've never met a time it didn't work. So this brings us to the next point. Ionic compounds must be written as a formula unit. What is a formula unit? Well, it is the simplest ratio between cation and anion. Smallest possible neutral unit. Here's what that means. Let's say, for example, what if you were trying to balance all the charges and you end up with this formula, Mg6PO4. What if you end up with that? Is that still a neutral compound overall? Would the charges balance out? They would. They would if you take the time to do the math. 6 times a +2, because you got 6 of these. 4 times a -3, you get -12 and +12, which adds up to 0, okay? But that's not simplest ratio, right? 6 and 4 can be simplified to 3 and 2, okay? You can divide both of those numbers, those subscripts, by 2. So that's what it means, simplest ratio. Always make sure you can't divide 3 and 2 by any number and get whole numbers, okay? So make sure that's a formula unit. And overall, it's neutral. How do I know it's neutral? We can always double, I'm going to erase. Always double check yourself. So I've got a -3 on phosphate, and I've got 2 of them. So -3 times 2 is -6. I've got a +2 on magnesium. I've got 3 of them. So +2 times 3 equals +6. And that adds up to 0. Questions on what we just did? So I'm teaching you how to write the formula for compounds. You can never change the charges. You can just manipulate the number of cations and anions that you need to write your formula so it's neutral overall.
Okay, can you like explain like how the switch thing works again? Because I didn't get it.
Okay, so it's these highlighted portions. I'm going to read this. The charge on this anion is the negative one. This ion is the anion. So the charge on the anion tells you the number of cations you need. You're always going to write the cation first, and when you write a compound, cation first, anion second. So the charge on phosphate is -3. You just take that number 3, drop the negative. That's how many cations you need, and you write that as a subscript in your formula. The charge on magnesium is a +2. So the 2 right there tells us how many it's on magnesium. We're going to switch it. We're going to apply that to the anion. That's how many anions we need in our formula. Does that help? I don't know who asked the question. Does that help, Kishan? No? Sorry, you're muted. I can't hear you if you're talking.
Yes, yeah, I'm good.
Okay. The more we practice it, I bet this will sink in deeper and deeper. So let's go over a couple of rules for writing ionic compounds, and we're going to do a lot of practice. All right, first, number one, write the cation first always, anion second. For example, we looked at a combination of calcium and oxygen earlier. It would be CaO, not OCa. Oxygen's the anion, calcium's the cation, cation first. So metal first, okay? Number two, do not include the charge on the ions. You write the charge if you're writing an ion, but when you're writing a compound, which is a combination of ions put together, you drop the charges. So CaO, not Ca2 plus O2 minus. Okay, not that. We don't need these. We can deduce the charges from knowing the position on the periodic table for each element. Okay. Next, use parentheses around the polyatomic ion if it has a subscript. Okay, meaning you need more than one. Okay, if you have to write a number for a subscript, that means you need more than one. For example, with the magnesium and the phosphate on the slide previous, we needed 2 phosphates. So we had to put that whole polyatomic ion in parentheses and write that subscript outside of it. Okay, that's what we did. So we had magnesium. We needed 3 of those, but that's just an element. So the 3 tells us we got 3 magnesiums. But phosphate has more than one element. So we got to put the whole thing, PO4. How do I know phosphate's PO4? This is where the rote memorization for those polyatomics come in. You're going to have these memorized before the exam, or at least have your polyatomic chart so you can quickly see, oh, phosphate's PO4. And we needed 2 of them. If we don't include the parentheses, look what happens. Mg3PO42. What does that look like? If I'm reading that, it looks like I have 42 oxygens, which is very incorrect, okay? That's why the parentheses help. It means everything within the parentheses is going to be multiplied by 2. We got 2 of them. Okay, what if I have aluminum and hydroxide? Hydroxide is a polyatomic. It is OH minus. So what if I have aluminum? Al, it's a main group 3. It's going to form a cation with a +3 charge. If I want to write a compound with this, cation first, anion second, I'm going to need 3 of these, right? Because a -3 and a +3 adds up to 0. I've got to write a neutral compound overall. So I'm going to write this compound. It'll be Al. I only need 1, aluminum. I got to put this in parentheses, OH, and then I need 3 of them. Okay, so use parentheses around polyatomics. This is only for polyatomics if you need more than 1. If you only need 1, you don't have to use parentheses. Questions on those rules? We're about to do some practice. I think it'll click. Okay, I've got four examples here. I want you to, above each of the word ion, so like above sodium ion and chloride ion, I want you to write the symbol for that ion. So let's do the first one together, sodium ion and chloride ion. Sodium is main group 1, it's Na, so you're going to write Na. It gave away its 1 valence electron, so it should have a +1 charge, so you just write plus. If you write +1, that's okay too. All right, now chloride should be Cl, that's chlorine. If you have a periodic table, this is going to help a lot. I think I have one right here below. So there's chlorine, it's main group 7 right here. So when it gets 1 more, it now has a -1 charge. So that's the symbols for the ions. Now, over here on the other side of the arrow, on the right side of the screen, I want you to write the compound, and then we're going to name it. So write the formula for the compound. Use these rules. These are rules for writing the formulas. And then we're going to name it. Name the compound overall. So anybody have the formula for sodium chloride? Remember that the compound has to be neutral, so you got to ask yourself, how many cations and how many anions do I need? All right, I'm seeing it in the chat. Yes. Oh, what happened? There it is. NaCl. You just need one each because you got a positive one and a negative one right here on your ions. So if I just got one of these and one of these, then my compound adds up to 0 when it comes to the charges. So how do we name this? When you're naming it, you just name the cation and then you name the anion. And you drop the word ion. So we're going to drop the word ion. So we just call this sodium. Yeah, Lucy said it. Sodium chloride. Remember, you do IDE if it's an anion. Sodium chloride. And we don't need Roman numerals here. Why?
It's not a transition metal.
Thank you, Keegan. Not a transition metal. So the charge of sodium, because it's a main group cation, is always predictable. Always going to be a +1. All right, next one, iron 3 ion and the sulfate ion. So here's what I notice. This does not end in IDE. Neither does this one, neither does this one. These are all polyatomics. So we're not going to use the IDE rule for naming these. You need to go look up the formula on the polyatomic chart to write out the ions for these. So iron 3 is obviously a transition metal, and that Roman numeral 3 tells us the charge. So it'll be Fe 3+, or you can write +3, doesn't matter. Sulfate. Sulfate, if you look at the polyatomic chart, is SO4, and the charge is -2. So how do we write the formula of the cation and the anion put together? How do we write the formula for the compound? You can use the switch trick here if you want. We've got a +3. Okay, so Gleanna says Fe2SO43. So she wrote this, Fe2 parentheses, because sulfate's a polyatomic. SO4, 3 of those. So if you do the switch trick, you take the charge on the cation, and that tells you the number of anions. Take the charge on the anion, that tells you the number of cations. So that's where the 2 and the 3. Now we could always double check. We got 2 irons. Each one is a +3. So 2 times +3 is +6. We got 3 sulfates. So 3 times each one is a -2. That adds up to -6, and overall, +6 and -6 balance to 0. It's a neutral compound. So how do we name this? We just drop the word ion. So it will be iron. Keep the Roman numerals if it's a transition metal. And you don't call it sulfide. It's sulfate because it's a polyatomic, and you just use the name for the polyatomics. Iron 3 sulfate. So you see how all the rules seem very simple starting out. But when you start writing all this out, it's all the rules come into play for all this different stuff. Okay, sodium ion and bicarbonate. Bicarbonate's a polyatomic. You're going to have to look the formula of that up. Again, I encourage you to memorize it, though. It'll help make things go quicker for the exam. I'm going to write it below because I'm a little bit tight on space. So we got sodium ion. We had that right above. That's Na+. Bicarbonate is HCO3, and the charge here is just a -1. So how many of each do you need? Go ahead and write the formula. You got a +1 and a -1. So it should be that if you just need one of each, Na. And do we need parentheses if we just need one bicarbonate? Do I need parentheses around it? That's correct. See head shaking. No. So then we name that, drop the word ion, sodium bicarbonate. And there was a problem in the book. Somebody, Madison, was that you? Madison was working a problem. Which problem was it that had typos in the back of the book? It was chapter 3. There was a problem working on stuff like this. That list of textbook problems that I gave you, I remember because bicarbonate was in it, and she was writing out the answers, and then she looked in the back of the book, and the answers weren't correct. And I looked at it too, and it is a typo, and I wanted to let you know what problem that was. Madison's going to type it in the chat when she remembers what problem it is. Let's go ahead and do one more. We got ammonium ion and phosphate ion. Ammonium ion and phosphate ion. Ammonium, guess what? That's a polyatomic as well. It doesn't end in ATE, but it's one of the cation polyatomics. Okay. Ammonium is NH4+. How did I know that? I just looked at the polyatomic chart. Okay. Phosphate is PO4 3-. So how many ammoniums, how many phosphates do you need? We're going to write the formula here. It's NH4. We're going to need 3 of these, right? 3 times +1 gives us a +3. And we've got to balance this -3. We just need one of those times -3 is a -3. That adds up to 0. So we need 3 of these. Whoops, that's a ugly parentheses. Okay. And then PO4. So that's how you write the formula for ammonium phosphate. And then we just drop the word ion. So it's just ammonium phosphate. Okay, so after 4 practice problems with polyatomics and transition metals and everything else, how do y'all feel about writing compounds? You're definitely going to have to do this on the exam. Feel good? Feel okay? All right. Did you find that problem, Madison?
Yes, it's 3.64.
Okay, 3.64. This has a typo in the back of the book. So if you want to know the answers to that, you can certainly email me and I'm happy to talk about it. But the answers in the back aren't correct if you're working those textbook problems. All right, there's more practice. These are just with ions. I'm going to let you do these on your own. I got one more slide to talk about a few properties of ionic solids and compounds. But I might make a video and walk through some of the answers to these and post it to Blackboard. Another practice problem, plenty of practice. Here's a slide I really want to get to. Properties of ionic solids. Okay, so a couple things in general I want you to know before we move on. Ionic compounds form what we call crystalline solids. Okay, we use the word molecule for covalently bonded stuff, and that's all chapter 4. So none of that's molecules is really not something we use for chapter 1 through 3 material. We don't call ionic compounds molecules. We call them crystalline solids. Some ionic compounds, so number 2, some of them dissolve in water and they form solutions that are good conductors of electricity. Okay, for example, you got sodium and chlorine. Remember when something becomes a cation, it is smaller. So if you're wondering why this purple sphere is smaller, it's because cations give away electrons, they become smaller. Remember, chlorine becomes the anion, and they get larger. The size of anions is larger than the size of the original atom. And what's nice is they orient themselves. They arrange themselves in this really ordered structure. All the negatives try to surround themselves with positives. All the positives try to surround themselves with negatives. And so things are really ordered and arranged. If we zoom in on one of these crystals, like this, what this figure is indicating, you see the atoms arranged like this. And these solutions, when these dissolve in water, sometimes the solutions conduct electricity weakly, but still it can. Okay, point number 3, ionic compounds have, you think, high or low melting or boiling points? What do you guys think? You got to ask yourself, are the ionic compounds held together by strong or weak bonds? If it's a strong bond, it's going to take a lot of energy to melt it or to boil it, a lot of heat. If it's a weak bond, maybe the molecule or the compound will fall apart easily. The correct answer here is they have very high melting and boiling points. Ionic bonds are very strong. It's a full positive charge and a full negative charge. Remember, opposites attract. So there's a lot of a strong attraction there in the bond of an ionic compound. Okay. Other compounds that share electrons and don't fully give away electrons, those bonds are weaker. They have lower melting points and boiling points, but not ionic compounds. It takes a lot of heat, a lot of energy to melt or to boil them. Lastly, number 4, ionic solids shatter when forcefully broken. Okay, glass, for example, is an ionic compound. We know glass shatters when it's broken. Okay, so I did have a poll question, but I want to spend time reviewing. So I want everybody to get out a sheet of paper and a pencil and a calculator. This is not a drill. This is real. I'm serious, everybody. Sheet of paper, pencil, calculator, blank sheet of paper, anything you can write on. Some of you are just looking at me. I'm for real. I'm going to time you, okay? I'm not trying to make your heart rate go up, or give you high blood pressure. I think it's good to practice, okay? Put away all your notes if you can. I know you're going to have your notes on the exam, but I challenge you to do this without your notes. Shut those to the side. We're gonna practice some things. We're gonna try to recall some things. It's gonna help you maybe identify, oh, I thought I was really good in this area. Maybe I'm not, okay? So I want to try to focus on the things that you're weak at on this. I expect everybody to be weak somewhere, and focus on those things as you spend time tonight and tomorrow studying for exam 1. So we have limited time. We don't have as much time as I want, and that's my fault because I was late. So if we don't get through all the answers to these, I promise I will post answers. We're going to work several problems, and I'm going to time you. We're going to move kind of fast, okay? So don't freak out. I will post answers to these things. All right, number 1. You're going to have 2 minutes. Write down, predict 9 topics or concepts from chapters 1 through 3 that you think will be on the exam. I'm starting the clock. Okay, you're about a minute in. If you can get more than 9, do it. Some are like, you done fried my brain and now you want me to think. Yes, I do. Okay, we're almost a minute and a half in. I'll give you like 20-ish more seconds. Okay, I see a lot of people starting to look up. Think you're good. 5 more seconds. We're going to move on. Again, we're going to come back to this, or I'll post answers somewhere. Let's move on. Next, we're going to classify matter. What is the difference between a heterogeneous mixture and a homogeneous mixture? Be concise, be short, but be specific. Give me an example. In simplest words, what's the difference between a heterogeneous and a homogeneous mixture? Okay, about 15 more seconds. Again, you don't have to write sentences here, just quick phrases. This is chapter 1. All right, we're going to move on. I know we're moving. So if you're like, oh, you're not giving me enough time, I'm very sorry. I'm going to post the answer. Okay. Next one, classify each of the following as either a chemical or physical change. This should be real quick. Don't write down the words you see on the screen. Just write 1 for chemical or physical, 2 chemical or physical. You can abbreviate P, C, P, whatever they are. Freezing a popsicle, roasting a marshmallow, bleaching, coloring your hair. See a lot of you sitting up. We're about to move on. 10 more seconds. All right, next one. These, you need your calculator. Grab your calculator. How many microliters are in 1.78 kiloliters? So these are prefixes and you need to convert from kiloliters to microliters. Now, micro isn't one I ask you to memorize. Remember, if you didn't get this already, 10 to the 6 microliters in 1 liter. Okay? You might need that in a minute too. All right, I've given you a full minute. I'm going to give you about 20 more seconds on this one. If you've already done that one, move on to the next one. Report the answer to the following problem in scientific notation. I want you to multiply these two numbers in scientific notation. What are the rules for multiplying numbers in scientific notation? All right, that's a minute and a half on the first problem. If you haven't finished that, I'm going to say go ahead and let's move on, even if you're not quite done. Scientific notation, what do you do? What are the rules? This was also from chapter 1, our measurements lecture. Make sure you're comfortable adding, subtracting, multiplying, dividing. Okay. Give you about 10, 15 more seconds on this, and then we're going to move on to the next one. And this will probably be the last one we do. I'm going to try to save 5 minutes to go through as many answers as I can. So when the clock hits noon exactly, we'll stop. All right, if you can, go ahead and start this next one as well. It says, this is a word problem. Dr. Michael prescribes 300 milligrams a day of a medicine, this should say patient, sorry, to a patient. Each pill has 1.5 times 10 to the power 5 micrograms of medicine. Remember, 10 to the 6 micrograms equals 1 gram. How many pills will the patient need for 7 days? If you're looking at this, thinking, where do I start? Remember your question says, how many pills? Write out relationships that you see. I see micrograms and milligrams, so you're going to have to convert between micrograms and milligrams at some point. Okay, give you about 30 more seconds on this. I want to save a few minutes for answers, and we probably won't get through everything, so I'll have to send y'all an email. Just give it your best shot. Okay, about 10 more seconds. And then I'm going to start going over some stuff. All right, let's wrap it up. Again, I know this was quick, but this is kind of how you're going to feel on exam day, right? You're going to feel rushed for time probably. So I think this was a good exercise and a good practice. And then how many of you are like, oh gosh, I see I have some things I need to review. Okay, that's the purpose of this too. Okay, 9 topics. You can type them in the chat. I'll try to catch the ones I can unless the chat blows up. I'm thinking of chapter 1. I know we talked about chemical versus physical changes. I know we talked about how to classify matter. Talked about the 4 signs of chemical changes. Okay. We talked about specific heat. I'm going to abbreviate specific heat. Those problems. We talked about temperature changes or conversions. Density. I see that. Yes, density. Anything else? Prefixes. And how to convert between micrograms and milligrams, so on and so forth. Complex conversions. Word problems. Okay. Chapter 2, we talked about atoms, their structure, and we talked about theory of atoms. Dalton's atomic theory, right? Structure is subatomic particles, protons, neutrons, electrons, and how those are arranged in an atom. Okay, what else did we talk about? We talked about the periodic table. How it's arranged, how it's ordered, how to count valence electrons, right? Main groups versus transition metals, so on and so forth. Octet rule was one of those things. We actually got to this for chapter 3. So I think we've hit 9 or more. We haven't even got to chapter 3, which is ions and compounds. Okay, ionic compounds, how to name them, how to write the formula. So take a screenshot of this if you want. That's several things that'll be on the exam. That's quite almost all of it, actually. There might be a few things here and there I didn't think of. Okay. What's the difference between heterogeneous and homogeneous? Homogeneous is evenly mixed. Okay, even throughout. You have multiple things mixed together, but they're distributed evenly. Example would be vanilla ice cream. Heterogeneous, the things are mixed, more than one thing, but it's not mixed evenly. Okay, it's not uniform throughout. The example is, what's a good example? Cookies and cream ice cream. Thank you, Mackenzie. I'm not going to take the time to write that, but cookies and cream ice cream. Sand, okay, sand and water, vegetable soup, things that are not, every bite would be different. All right, classify each of the following, either chemical or physical. Freezing a popsicle. Physical, roast, keyword there is freezing. Roasting a marshmallow. Yes, if you got to go, it's 12:05. I know it's 12:05. If you got to go, thank you for joining. I'll send these answers via email. If you want to stick around, I'm going to spend a few more minutes going through our answers. Roasting a marshmallow is chemical. Okay, keyword there, roasting. Bleaching your hair. What do y'all think? Yep, definitely chemical. Okay. The substances are not different when you, or sorry, the substances change. The chemical composition changes on when you roast a marshmallow and bleach your hair. Okay. How many microliters are in 1.78 kiloliters? So we need this relationship, and we also need this one, 1,000 liters in 1 kiloliter, right? So we got 1.78 KL. I'm going to convert to liters. So for every 1 kiloliter, there's 1,000 liters. And for the last conversion to microliters, I want to cancel liters. So for every 1 liters, it's 10 to the 6 microliters. Nija, or Nij, I think is how you say it. I'm sorry, Nij got 1.78 times 10. It should be to the positive 9. There's a lot of microliters and kiloliters, so not to the negative 9. Yep, thank you, Keyshawn, to the positive 9 microliters. That's what you should have gotten for that one. You're multiplying by 1,000, multiplying by 1,000,000. Ultimately, you're multiplying by 1,000,000,000. Okay. Okay, multiplying numbers in scientific notation. Remember, you're going to multiply the base unit numbers, okay, the digits, and you're going to add the exponents, okay? So you multiply the numbers and then you add the exponents. If you got to go, feel free to head out. We're past time. If you want to stick around, that's great. So 2.03 times 7.44. What did y'all get? 2.03 times 7.44. Was that, oh, hold on, Glenn already got us all the way there. It should be 15 point something, because I wanted to make a point with this one. 2.03 times 7.44. I got 15.103. And then you add 11, okay, 11 plus -3, and you should get 8, right? So that's times 10 to the 8. So this is not a number between 1 and 10, though. 15 is above 10. So we got to move the decimal place right there. And when you move the decimal place left, the exponent increases. So this should actually be the right way to do this is 1.5, we'll just say 1.51 times 10 to the power of 9. Questions on that? I see some eyebrows raised.
So it's 10 to the power of 9 because we had to move the decimal?
Yes, when you do the multiplication of 2.03 and 7.44, you get 15.103, but 15 is not a number between 1 and 10, so you do have to manipulate that one more time. Move the decimal to the left one place, Danielle.
Okay.
Yep. Okay, last one. This is the last one we got to. Dr. Michael prescribes this problem. So I'm going to write some relationships out. 300 milligrams a day, that's 1. 300 milligrams of drug in 1 day. And we see that each pill, so this will be in pill form, 1 pill has 1.5 times 10 to the power of 5 micrograms. And then we got to go for 7 days. Okay, so that's a piece of information we'll need as well. How many pills? 7 days. So I see milligrams and micrograms, and this is all talking about the medicine. So we're going to have to convert between milligrams and micrograms. I know there's 1,000 milligrams in 1 gram. I know there's 10 to the 6 micrograms in 1 gram. So I'll just move that relationship right down here. Now, because these both equal 1 gram, I'm just going to combine these. There's 1,000 milligrams and 10 to the 6, a million micrograms. You can simplify that if you want, but you don't have to. So the question says how many pills? That's what I want on my answer, units of pills. So I'm going to pick the relationship that has pills in it. If you didn't do it this way, that's fine. But here's how I'm going to do it. So 1 pill on top, 1.5 times 10 to the 5 micrograms on bottom. I want to cancel micrograms because I don't want micrograms in my answer. So the way I can do that is with this relationship. It's the only other relationship that has micrograms in it. I'm going to write this with 10 to the 6 micrograms on top so that micrograms cancel. And I'm going to write it with 1,000 milligrams on bottom. Now I want to cancel milligrams. I don't want milligrams in my answer. I just want how many pills. So this is the other relationship that has milligrams in it. I can use this to cancel milligrams. So I'm going to write 300 milligrams on top, 1 day on bottom. Milligrams cancel there and there. Now I want to cancel days. I don't want to know how many pills per day. I got to go for 7 days. Okay, so we're going to multiply by 7 days. If you said 7 days per week, that's fine too. Different people I've seen do this different ways. Days cancel. You don't have to do per week. Now you just do all the math. How many pills did y'all get? Haley said 14. Do not forget this initial 1 right here. You got to do 1 divided by that big number. If not, you'll get a wrong answer. So if you do all this, you should get 14 pills. So maybe the doctor wants you to take 2 a day, I would imagine. Okay. All right, everybody. Again, I'm terribly sorry that I was late. That's totally my fault. But I hope if you have any questions, you can stick around. I'm happy to answer those. Good luck on the exam.